Module 4, Lecture A, Linear Regression. By the end of this lecture, you will be able to describe linear regression as fitting a line or plane to numeric data, interpret the meaning of regression coefficients in simple examples, and assess the quality of a linear regression fit using visual patterns of errors. Lines for prediction. Visualizing data relationships. To understand how two numeric quantities are related, we can plot them on a graph and look for patterns. For example, we might plot each student's study hours against their exam score as a point on the graph. If the points tend to rise as we move to the right, this suggests that more study hours are associated with higher scores. This kind of plot is a basic tool for visualizing relationships in data, and introduces the idea of fitting a line through the points to describe that relationship. Scatter plots are useful for examining how two measurements relate to each other, such as physical activity and blood pressure, work experience and income, or temperature and electricity use. Each point on the plot represents a paired measurement. When the points form an upward trend, it suggests a positive relationship, and when they form a downward trend, it suggests a negative relationship. If the points are scattered randomly with no clear pattern, there is likely no strong relationship between the two variables. When you visualize relationships in data, you should look beyond simple trends and pay attention to patterns that affect how well a straight line can summarize them. A narrow, straight band of points suggests a line might fit well, while a curved pattern suggests a line could miss important features. Clusters of points may indicate different groups, and outliers can pull the line away from the main pattern. Noticing these details helps you judge how the variables relate, and whether a straight line is a good choice for prediction, which is essential groundwork for linear regression. Python code. Visualizing data relationships. This script helps you see simple numeric relationships by plotting synthetic data for study hours and exam scores. Its main goal is to show how scatter plots work and how to spot visible trends in the data. As you look at the points, focus on how changes in study time relate to changes in exam performance. We begin by importing two key Python libraries, one called NumPy for efficient numerical calculations, and another called matplotlib pyplot for creating visualizations. These tools allow us to process and analyze data, and then turn that data into plots. Using them together is essential for exploring and visualizing relationships in our dataset. We start by setting a fixed random seed using the numerical computing library so that any random numbers generated are the same every time the script runs. This makes the results reproducible, meaning we can reliably repeat experiments and get identical outcomes. It is especially helpful when checking our work, debugging, or sharing code with others, because everyone will see the same results under the same conditions. We use a function from the NumPy library to create an array of study hours, generating 20 evenly spaced values from 0 to 10. Each value in this array represents how many hours a student studied. This gives us a simple, continuous range of study times that we can use as the basis for our analysis. We create exam scores that generally rise with study hours by starting from a base score of 50 and adding 5 points for each hour studied, forming a simple linear trend. To make the data more realistic, we then add random noise drawn from a normal distribution with mean 0 and standard deviation 5. This noise is generated to match the size of the study hours data, so each score gets its own small random adjustment. The result is a set of scores that usually increase with more study time, but still show natural variation. This code prints a short summary of the dataset we just created. It reports how many students are included based on the length of the study hours data, and notes that each student has both study hours and an exam score. This quick check helps confirm that the data is set up correctly before we move on to visualizing it. We use an assertion to check that the study hours and exam scores arrays have the same shape. This ensures that every study hour value has a matching exam score. Having this one-to-one pairing is necessary for correct plotting and analysis. If the shapes do not match, the assertion triggers an error, warning us that something went wrong during data preparation. We start by creating a scatter plot to explore how study hours relate to exam scores. Using a plotting library, we open a new figure window and set its size to 6 by 4 inches. This size makes the chart large enough so the individual data points and any overall patterns in the scores are easy to see. We use a scatter plot from the matplotlib library to show each student as a point on a graph. The horizontal axis represents study hours, and the vertical axis represents exam scores. Each point is drawn in blue and labeled as students, so the legend clearly identifies what the points represent. In matplotlib, we label the x-axis as hours studied to show that it represents how many hours each student studied. We label the y-axis as exam score to indicate that it shows the score each student received. These axis labels make it clear what the data points in the scatter plot represent and help viewers quickly understand the relationship being shown. We add a title to the plot to clearly describe the relationship being shown. In this case, the title, Visualizing Relationship Between Study Hours and Exam Scores, tells viewers that the scatter plot shows how study time relates to exam performance. This context helps people immediately understand what the data represents. Including such a title makes the plot more informative and largely self-explanatory. To make the plot easier to read, we add a grid with dashed, semi-transparent lines so viewers can more easily track data points along the axes. We also include a legend that explains what the plotted points represent. In this example, the legend clarifies that the points correspond to students' data. Together, the grid and legend make the visualization clearer and more informative. To finish the visualization, we call the show function from the plotting library to render and display the scatter plot. This opens a window with the chart so we can see the relationship between study hours and exam scores. It is the final step in the process, making the data and any trends easy to view and interpret. This script creates a scatter plot to show how study hours relate to exam scores using synthetic data. Study hours range from 0 to 10, and exam scores generally increase as study time goes up, with some random variation added to mimic real life. Each point on the graph represents a student, with study hours on the horizontal axis and exam score on the vertical axis, along with labels, a title, and a grid for clarity. When you run it, you see a clear positive correlation, meaning that more study time usually leads to higher exam scores, even though the data are not perfectly aligned. Line as simple summary. When we draw a line to summarize data, we are turning a scattered set of points into a clear overall trend. For example, if we plot students' study hours against their exam scores, the points may look messy and inconsistent. A line through these points shows the general pattern that more study time tends to lead to higher scores. This line does not pass through every point, but it represents the average relationship and makes the data easier to understand and explain than looking at all the individual points. A line can be viewed as a summary of data that separates the main pattern from random variation. For example, when relating house price to size, a fitted line highlights the overall trend that larger homes tend to cost more, even though other factors like location and condition cause individual prices to differ. The line represents the predictable part of the relationship, while the distances from the data points to the line represent the unpredictable influences. In this way, the line helps us distinguish the signal from the noise in the data. Using a line to summarize data is useful because it captures the main pattern between two variables and lets us predict new outcomes. Once we find a line that reflects their relationship, we can make informed estimates for new situations, such as recovery times for patients of different ages or electricity demand at various temperatures. Even though this line does not show every detail, it highlights the overall trend and strength of the relationship, which supports better decisions and clearer communication. Many inputs, one line. Linear regression can be seen as drawing a straight line through data points on a graph to predict an output from an input. In many real situations, though, the output depends on several inputs at once, such as a house price depending on size, age, distance from the city center, and school quality. In these cases, linear regression still works by combining all inputs into a single rule that forms a flat surface in higher dimensional space, called a plane or hyperplane. This fitted surface best matches the data and lets us predict outcomes while taking all relevant inputs into account together. In linear regression, each data point has several input coordinates, such as different features, along with an outcome value. The model finds a flat surface in this multi-dimensional space that best fits all the data points. To make a prediction, you plug in specific input values and the model outputs a predicted result, like a house price. No matter how many inputs there are, the model always applies the same linear rule, adding up the inputs with fixed weights to produce a single prediction. Linear regression models situations where several numeric inputs combine to influence a single outcome in a consistent, additive way. Each input, such as study hours, grades, attendance, temperature, or budget, contributes its own steady effect, and these effects add together. Geometrically, each new input adds a dimension, but the model still forms one flat surface that summarizes the overall pattern in the data. In this sense, linear regression finds a single coherent geometric object running through many points and uses it as a simple rule for making predictions from multiple inputs. Interpreting regression coefficients. Single feature effect. In a linear regression model, the single feature effect describes how one predictor influences the outcome, while other factors are held constant. For example, the coefficient for study time tells you how much the exam score is expected to change for each additional hour of studying. A positive coefficient means that increasing the predictor, like study time, is associated with higher outcomes, while a negative coefficient means that increasing it, such as stress, is associated with lower outcomes, like poorer sleep. This coefficient gives a clear numerical summary of both the direction and strength of the relationship between the predictor and the outcome. To interpret a regression coefficient, connect it to the real-world units of the variables. It tells you how much the predicted outcome changes when the input increases by 1 unit, while other factors stay the same. For example, if electricity use is predicted from home size and the coefficient is 3, then each extra square meter adds 3 kilowatt-hours per month. If income is predicted from years of experience and the coefficient is 2,000, then each additional year increases income by 2,000 currency units. The sign of the coefficient shows whether this change is positive or negative. In regression models, the effect of a single feature shows an average trend in the data, not a precise prediction for each individual case. For example, larger houses may generally cost more, and higher physical activity may be linked to lower resting heart rates, but there will always be exceptions. These models capture typical patterns that help guide decisions, while we must remember that individual outcomes can differ due to unique circumstances and unmeasured factors. Python code, single feature effect. This material introduces single-feature linear regression using a very small dataset that relates study hours to exam scores. The goal is to show how the regression coefficient, or slope, captures the effect of that one feature on the outcome. By focusing on this simple example, you can clearly see how changes in study time are reflected in predicted scores through the slope value. We begin by importing two key Python libraries used throughout this script. We use a numerical computing library to handle arrays and perform efficient mathematical operations. And we use a plotting library to create visualizations. Together, these tools provide the foundation for manipulating data and displaying the results in graphical form. We begin by creating a small synthetic dataset to represent study hours, using a sequence of floating point numbers from 1 to 6. This sequence acts as our independent variable, indicating how many hours a student studies per week. Using floating point values helps maintain precision in later calculations. With this dataset in place, we can then apply linear regression to explore how study hours relate to exam scores. We use a NumPy array called scores to store exam results that increase roughly in a straight line pattern as study hours increase. The array holds the floating point values 52, 57, 63, 68, 74, and 79. This simple dataset lets us explore how changes in study time might affect exam performance and provides a basis for basic regression analysis. We use an assertion to check that the hours and scores arrays have the same shape, meaning each study hour has a matching exam score. This check is important because it protects the integrity of the data used in later calculations. If the shapes do not match, the assertion stops the program and raises an error. This prevents the script from continuing with inconsistent or mismatched data. To build the design matrix for linear regression, we first create a column of ones that has the same length as the study hours data. This column represents the intercept term in the model. We then use a column stacking operation from a numerical library to combine this column of ones with the study hours values. The result is a two-dimensional array where each row is a data point. The first column is the intercept, and the second column is the number of study hours. This matrix form is required to apply the normal equation and compute the regression coefficients. In the normal equation method for linear regression, we first multiply the transpose of the data matrix by the data matrix itself. This product captures how the input variables relate to each other. We then take the inverse of this product. Inverting this matrix is what allows us to solve for the regression coefficients that give the best fit line by minimizing the error in the linear model. In this step, we compute the final coefficients of our linear regression model, which include both the intercept and the slope. We do this by applying the normal equation, which uses the design matrix and the observed scores. Specifically, we multiply the inverse of the design matrix multiplied by its transpose with the transpose of the design matrix times the scores. This calculation gives us the best fit line that minimizes the difference between the predicted and actual scores. We separate the two regression coefficients to make their meanings clearer. The first value, called the intercept, is the predicted exam score when study hours are 0. The second value, called the slope, tells us how much the exam score is expected to increase for each additional hour of study. Looking at these two values separately helps us clearly describe how study time affects exam performance. We begin by reporting the slope for the hours of study feature, which tells us how many exam score points are expected to increase for each additional hour of studying. This value is rounded to 2 decimal places to make it easier to read and interpret. We then restate this in more intuitive terms, explaining that every extra hour of study adds roughly that many points to the exam score. This highlights the practical impact of study time on performance. To plot the fitted regression line, we first create a sequence of study hour values that covers the full range of the data. We use a numerical tool to generate about 50 evenly spaced points between the minimum and maximum observed hours. These points are then fed into the regression model to produce predicted exam scores. Plotting these predictions against the generated hours gives a smooth line that represents the model's estimated relationship between study time and exam performance. To find the predicted scores from our linear regression model, we use the fitted line equation. We start with the intercept and add the slope multiplied by each value of study hours. This calculation gives a predicted exam score for every hour value. Together, these predictions form the straight line that represents our linear regression model. We start by making a scatter plot to show how study hours relate to exam scores. Each data point is plotted in blue and labeled as observed scores, so it is easy to distinguish them. This visual representation helps us see the pattern in the data and later judge how well a regression line matches the actual scores. We use a plotting function from a graphing library to draw the regression line that shows the predicted relationship between study hours and exam scores. The horizontal values for this line come from the study hours data, and the vertical values are the corresponding predicted scores. We color the line red so it stands out clearly from the data points, and we give it a label called fitted line so it can be easily identified in the plot legend. We use matplotlib to label the x-axis as study hours per week to show that it represents how many hours a student spends studying. We label the y-axis as exam score to indicate that it shows the scores students achieve on exams. These axis labels make the plot easier to interpret and help viewers quickly understand the relationship between study time and exam performance. We title the plot Single Feature Effect of Study Hours on Exam Score to clearly state what the visualization is about. This title tells the viewer that the plot focuses on study hours as the only feature being examined. It highlights how changes in the number of hours studied relate to changes in exam scores. As a result, listeners can immediately understand that the purpose of the plot is to show the relationship between study time and exam performance. The code uses the legend feature from the plotting library to add a legend to the graph. This legend labels the observed data points and the fitted regression line. As a result, viewers can easily tell which elements on the plot represent the original data and which represent the regression model. The final step of the script uses a plotting library to open a window that displays the results. In this window, you see a scatter plot of study hours versus exam scores, along with the fitted regression line. This visual output brings together all the previous calculations and lets you clearly see how study time relates to exam performance. It also shows the effect of using a single feature regression model in a way that is easy to interpret. This script shows how study hours affect exam scores using a simple linear regression model. It builds a small dataset where scores increase with the number of hours studied, then constructs a design matrix with an intercept term and the study hours. The regression coefficients are computed using the normal equation, giving an intercept and a slope that indicate how many points the score increases for each additional hour of study. The script prints this slope for interpretation and displays a scatter plot of the data with the fitted regression line to visually illustrate the relationship between study time and exam performance. Understanding the intercept. In a linear regression model, the intercept is the predicted outcome when all explanatory variables are 0. For instance, if you predict electricity bills from apartment size, the intercept represents the bill for an apartment with 0 size, even though that situation is not realistic. Despite this, the intercept is important because it anchors the regression line vertically and allows the model to fit the data as well as possible. In other words, it is mathematically essential for achieving the best least squares fit, even if it does not correspond to a meaningful, real-world case. In a regression model, the intercept often has a meaningful interpretation that helps you understand the situation. It represents the expected outcome when the predictor variables, such as study hours or advertising spend, are 0. For example, it can show a student's baseline exam score with no studying, or a company's expected sales with no advertising. In this way, the intercept summarizes the baseline level of performance or demand and provides useful information for planning and decision-making. When interpreting intercepts in regression models, you need to consider the range and scaling of the predictor. If a predictor value of 0 is outside the data you actually observed, the intercept may not represent a realistic situation, such as predicting income for 0 years of work experience when your data does not include that case. When you transform predictors, for example by centering them around their mean, the intercept instead represents the predicted outcome at the average predictor value. Recognizing these details helps you decide whether the intercept has a meaningful interpretation or is simply a mathematical part of the model. Units and scaling. When interpreting regression coefficients, always connect them to the measurement units of each variable. A slope only has meaning when you state how much the outcome changes for a 1-unit change in the predictor. For example, if monthly electricity cost is modeled from household size, a slope of 15 means each additional person adds $15. If you instead measure household size in groups of 10, the numerical value of the slope becomes smaller because 1 unit now represents a much larger change in size. The underlying relationship does not change, only the coefficient's value changes with the units. When comparing regression coefficients, you must pay attention to the units of measurement. A coefficient can look larger or smaller simply because one predictor is measured in big units, like hours, and another in small units, like single problems. If you rescale a predictor, such as using tens of hours or sets of 50 problems, the numerical value of the coefficient changes, but the model's predictions do not. What matters is how you interpret it, so always describe the effect in terms of the new units, such as per additional hour or per set of 50 problems, rather than focusing only on the raw coefficient value. Rescaling variables in regression helps make coefficients easier to interpret, because their values depend on the units used. For instance, changing floor area from square feet to hundreds of square feet changes the slope from a small number per square foot to a larger, more intuitive number per 100 square feet, even though the underlying relationship is the same. Analysts also often standardize predictors so that 1 unit represents 1 standard deviation, which shows how much the outcome changes when moving from average to 1 standard deviation above average. The key idea is to always consider the scale and units of your variables when interpreting regression coefficients. Visual error patterns, prediction versus actual. In a linear regression model, each data point has an actual outcome and a predicted outcome, and we can judge the model by comparing these two. One way to do this is to plot actual values on the horizontal axis and predicted values on the vertical axis. If the model is accurate, the points will lie close to a straight reference line where predictions equal actual outcomes. For example, when predicting house prices, each house appears as a point showing how close the predicted price is to the real selling price. A tight cluster of points around the line means the model is capturing the main pattern in the data well. A prediction versus actual plot helps reveal patterns that simple metrics like average error can miss. By comparing predicted values to true outcomes, you can see where a model consistently overestimates or underestimates results. For instance, you might notice that long recovery times in healthcare are predicted too low, or that low exam scores are predicted too high. This visual check shows where the model is trustworthy and where its predictions may be misleading. Prediction versus actual plots help you see when a linear model may be too simple. If the points follow a curved pattern instead of lining up around a straight line, that suggests the true relationship is nonlinear, and the model may underpredict or overpredict in certain ranges. If the spread of points grows as the actual values increase, it means errors are larger at higher values, which can be important for decisions. By recognizing these patterns, you can judge when a linear model is trustworthy and when its limitations might affect your results. Python code, prediction versus actual. This script provides a simple visual comparison between predicted and actual values. It is designed to help you see and understand error patterns in linear regression models. To keep the demonstration clear, it uses a very small set of synthetic data. Overall, it offers an easy way to grasp how well a linear regression model is performing. We start by importing the numerical library that efficiently handles numbers and arrays, and then we bring in the plotting module from the visualization library. Together, these tools allow us to perform numerical computations and create visual representations of data. Setting them up at the beginning prepares the script to carry out the data analysis and plotting tasks it is designed to perform. We begin by setting the random seed in the numerical library to the value 42, so that any random numbers generated are the same each time the program runs. This makes the code deterministic, meaning it will always produce identical results under the same conditions. Such reproducibility is important because it allows us to reliably debug the program and verify that its behavior is consistent over time. We begin by creating a simple set of input data, using a numerical tool that generates evenly spaced values. In this case, we produce 30 numbers spread uniformly between 0 and 10. These numbers serve as our feature values and form the basic data set that we will use for later analysis and simulation. We generate the outcome values by applying a simple linear rule to the features. Each feature value is multiplied by 2, and then 3 is added. To make the data more realistic, we also add random noise. This noise comes from a normal distribution with mean 0 and standard deviation 2, and it has the same shape as the feature values. This process creates outcomes that follow a clear linear pattern but are not perfectly predictable. We use a simple linear model to generate predicted values from our features. For each feature value, the model multiplies it by 1.7 and then adds 4. This method is deliberately not perfect, so we can see how predictions can differ from actual outcomes in realistic situations. The resulting predicted values are stored in an array for later comparison with the true values. The code first checks whether the actual and predicted arrays have the same shape, meaning they contain the same number of values arranged in the same way. This is important so that each actual value can be directly compared with a corresponding prediction. If the shapes do not match, the code raises a value error to indicate a data mismatch that must be fixed before any further analysis can be done. The script first prints a short header message to the console to let the user know what is coming next. This message explains that the program will show the first 5 pairs of actual values and their corresponding predicted values. It serves as a simple introduction so the user understands that a comparison between real and predicted data will follow in the output. The code looks at the first 5 data points, and for each one prints a short summary. It shows the index of the data point, the actual value, and the predicted value. Both values are rounded to 1 decimal place to make them easier to read. This allows you to quickly compare the actual and predicted values side by side for the initial entries in the dataset. We begin by creating a new figure using the plotting library and set its size to 6 by 6 inches so the plot is clear and easy to read. This step prepares the visual space where our data will appear. By defining the figure in this way, we create a balanced area that makes it easier to visually compare the predicted values with the actual values. We create a scatter plot using a plotting library to compare actual and predicted values, placing the actual values on the horizontal axis and the predicted values on the vertical axis. Each data point is shown as a blue circle so we can visually assess how closely the predictions match the true values. The circles are made slightly transparent to make overlapping points easier to see. We also assign the label data points so these markers can be identified clearly in the plot legend. To draw the ideal reference line where predictions match actual values, first find the smallest value across both the actual and predicted data, and use this as the starting point. Then find the largest value across both sets, and use this as the endpoint. These two values define the range of the line, ensuring it covers all observed data. This line then serves as a visual benchmark to see how closely the predictions align with the actual outcomes. We use a numerical tool to generate a sequence of evenly spaced values between the smallest and largest numbers found in both the actual and predicted data. These values define a straight reference line that represents perfect prediction. By plotting this line alongside the model's predictions and the true values, we can visually assess how closely the predictions match the ideal case. We draw a line to show perfect predictions by plotting the same values on both the horizontal and vertical axes, which creates a diagonal. This line is colored red and given a dashed style so it stands out clearly. We also assign it the label perfect prediction so it can be easily identified in the plot legend. We label the horizontal axis as actual values to show it contains the true data points, and we label the vertical axis as predicted values to show it contains the model's estimates. These labels make it clear which values come from real outcomes and which come from the model. This helps listeners quickly understand that the graph is comparing actual results with the model's predictions. We add a title to the plot to highlight that it compares predicted values with actual values. This title tells viewers right away that the goal is to show how closely the simple linear model's predictions match the real data points. By clearly labeling the plot, we make the purpose and context of the visualization easier to understand. This helps anyone reviewing the graph quickly grasp what the analysis is about. The code uses the legend feature from the plotting library to add a legend to the graph. This legend shows labels for the data points and the reference line. By clearly indicating what each element represents, it makes the plot easier to read and interpret. Setting the plot's aspect ratio to be equal makes 1 unit on the horizontal axis the same visual length as 1 unit on the vertical axis. This creates a true 1-to-1 scale between the axes. As a result, it becomes easier to visually compare actual and predicted values and to judge how closely the predictions match the real data points. The final line of the script calls the show function from the plotting library to open the plot window. This step actually renders the visualization that has been prepared. It lets us see the comparison between predicted and actual values. In short, it is the last command that makes the graph appear to the user. This script creates a simple visual comparison between predicted and actual values using synthetic data. It first generates data with a roughly linear relationship and some random noise, then computes predictions using a slightly different linear model. The script prints a few sample pairs of actual and predicted values, and then plots them on a scatter plot, with actual values on one axis and predicted values on the other. A red dashed line shows where perfect predictions would lie, and labels and a legend clarify the plot. By looking at how the points deviate from this line, you can quickly assess prediction accuracy and see patterns in the errors. Residuals as differences. In linear regression, residuals are the differences between the model's predicted values and the actual observed values. For each data point, you take the observed value and subtract the value predicted by the fitted line. You can think of a residual as the small adjustment needed to make the prediction match the real outcome. For instance, when predicting house prices from square footage, the residual is the gap between the actual selling price and the predicted price. Residuals therefore provide a concrete measure of the model's error for each observation. Residuals describe both the direction and size of a model's prediction error. A positive residual means the actual value is higher than the prediction, so the model underestimated. A negative residual means the actual value is lower than predicted, so the model overestimated. The size or magnitude of the residual shows how far off the prediction is, measured in the same units as the outcome, such as dollars or exam points. For instance, a residual of +5 on an exam score means the student scored 5 points higher than the model expected. Plotting residuals helps you visually judge how well a model fits your data. Residuals are the differences between actual and predicted values, and for a good model, they should be small and spread evenly around 0. If you see patterns, such as consistently positive residuals for larger houses or older patients, it suggests the model is systematically wrong for those groups. This means the model may be missing important factors or misestimating certain ranges, which you can detect by examining the residuals. Warning signs in residuals. When you check residual plots for a linear model, you want the residuals to look like random scatter. If instead they show a clear pattern, such as curving up and down as predicted values increase, it means the straight-line model is not capturing the true relationship. This often happens when the real relationship is nonlinear, like a U-shaped link between study time and exam scores. In such cases, the linear model's predictions are unreliable, so you should question whether a straight-line model is appropriate whenever you see smooth curves or repeating structures in the residuals. When examining residual plots, an important warning sign is non-constant variance, where the spread of residuals changes as the predicted values increase or decrease. Ideally, residuals should be evenly scattered around 0, forming a consistent band across all prediction levels. If you see a funnel shape with small residuals for low predictions and much larger residuals for high predictions, it means the errors grow with the size of the prediction. This pattern suggests the model is less reliable for certain ranges of the data, so any decisions based on it should be made cautiously or with an improved model. Patterns in residual plots, such as clusters, outliers, or long streaks, often reveal problems in a model or the data. Distinct groups of residuals can indicate a missing variable or unmodeled factor, like different types of customers or machines. Long runs of positive or negative residuals suggest time-dependent errors, which are especially important in time series data. Very large residuals, far from the rest, may point to outliers or data quality issues, such as incorrect measurements. Noticing these patterns helps you refine the model or improve data collection before drawing strong conclusions. Python code, warning signs in residuals. This script provides a simple way to visualize residual warning patterns in linear regression. It clearly shows how the curvature and spread of residuals change. This makes it easier for beginners to judge whether a linear regression model is an appropriate fit. In this script, you are working in Colab, a cloud-based Python environment where common libraries are already installed. This means you do not need to manually install tools like NumPy, Pandas, matplotlib, or Seaborn to perform numerical computations and create plots. If you were running the same code on your own computer or another environment, you might need to install these libraries yourself to ensure everything works correctly. We start by importing a numerical computing library that lets us work efficiently with arrays and perform mathematical calculations. We also import a plotting module from a visualization library. This plotting tool allows us to create graphs and visualize patterns in our data. Together, these two libraries provide the core tools we need for numerical analysis and data visualization in our work. We set the random seed to the value 42 using the random tools from the NumPy library. This fixes the sequence of random numbers the script produces. As a result, every time we run the code, it generates the same random values. This makes our results reproducible and consistent across different runs. We create a sequence of predictor values using a numerical tool that generates 60 evenly spaced numbers from 0 to 10. This sequence acts as our independent variable in the example. It provides a simple, regular set of input values that we can use to model relationships in the data. These values also make it easier to visualize how the model behaves across the entire range from low to high inputs. We use a simple linear rule to make our predictions. For each input value, we multiply it by 2 and then add 3 to get the predicted output. This creates a straight line that acts as our baseline model. We then compare this baseline line to the actual data, so we can see how the predictions differ from the true values and look for patterns in those differences. To intentionally break the linearity assumption, we define a curved true relationship between the predictor and the outcome. We start with a simple linear part, which is 2 times the predictor plus 3. Then we add a quadratic part, which is 1/2 of the square of the difference between the predictor and 5. This extra curved term makes the overall relationship nonlinear and more complex than a straight line. We create random noise using a normal distribution with a mean of 0 and a standard deviation of 2, shaped to match our input values. This noise is then added to the true curved values. Doing so introduces variability into the data and mimics the kinds of imperfections we see in real-world measurements. We create the observed values by adding random noise to the true curved values. This step mimics real-world data, where measurements are never perfectly clean. By doing this, we generate noisy observations that we can later compare with the values predicted by a linear model. Residuals are found by subtracting the model's predicted values from the observed values. They show how far the model's predictions are from what actually happens. By examining these differences, we can judge how accurate the linear model is and look for patterns that suggest it may be missing important structure, such as nonlinear relationships. Before plotting residuals, the code checks that the residuals array has the same shape as the array of x values. This guarantees that each residual is correctly paired with a specific x value, which is essential for accurate plots and analysis. An assertion is used for this check, so that if the shapes do not match, the code immediately raises an error and prevents misleading visualizations. We begin by setting up a plotting area using the subplots function from matplotlib, which creates a figure and an axis for our graph. This provides the canvas on which we will draw the residual scatter plot. We also specify the figure size as 6 by 4 inches to give a clear, manageable space for viewing the data. A scatter plot of residuals versus predicted values is used to check how well a linear model fits the data. The predicted values are placed on the horizontal axis, and the residuals on the vertical axis. By looking at the pattern of points, we can see whether the residuals appear random or show structure. A random cloud of points supports the model assumptions, while visible patterns may indicate problems such as nonlinearity or changing variance. This step adds a horizontal reference line at 0 on the plot, using the axis tool for drawing horizontal lines. The line is styled as a thin black dashed line. Its main purpose is to mark the zero level clearly, so you can easily see how the residuals deviate from zero and detect any systematic bias in the pattern. The code sets the x-axis label of the plot to indicate that it shows the predicted values from the linear model. This tells the viewer that the horizontal axis represents the model's predicted outcomes. With this label, it becomes clear that the residuals are being plotted against these predictions, which helps in correctly interpreting the plot. The code sets the y-axis label of the plot to indicate that it shows the residual, which is the difference between the observed value and the predicted value. This label clearly states what the vertical axis represents. As a result, it becomes easier to interpret the plot and understand how the observed data compare to the model's predictions. The plot title, Residual Plot Showing Curvature Warning Sign, tells the viewer that the key feature to notice is curvature in the residuals. This curvature signals possible problems with the linearity assumption in the model. When residuals curve instead of scattering randomly, it suggests that a nonlinear relationship may fit the data better. Clearly labeling the plot in this way helps communicate this diagnostic message to anyone interpreting the model. The code uses the tight layout feature in matplotlib to automatically adjust the spacing in a plot. This helps prevent labels, titles, and other elements from overlapping. As a result, the plot looks cleaner and is easier to read. Overall, it improves the clarity and presentation of the visualization. The code prints a short message that highlights warning signs in the residual plot. It explains that the residuals follow a curved pattern, which suggests the linear model is missing some nonlinearity in the data. This means the current linear fit may not capture all the underlying trends. As a result, the user is encouraged to consider a more complex model. The code uses a plotting library to create a residual plot, which shows the differences between the observed values and the values predicted by the linear model. By looking at this plot, you can visually check for patterns or unusual points in the residuals. Such patterns may reveal problems with the model, like nonlinearity or changing spread of errors that suggest the linear model may not be appropriate. This script shows how residuals can reveal problems in a linear regression model. It creates predictor values and a true relationship that is curved rather than perfectly linear, then adds noise to generate observed data. The model fits a straight line and computes residuals as the difference between the observed values and the model's predictions. When the residuals are plotted against the predicted values, they form a clear curved pattern, indicating that the linear model is missing an important nonlinear component. This pattern shows that the model does not fully capture the underlying data and that a more complex model is needed. In this lecture, you learn to describe linear regression as fitting a line or plane to numeric data, interpret the meaning of regression coefficients in simple examples, and assess the quality of a linear regression fit using visual patterns of errors. In the next lecture, Lecture B, we will go over linear classification.
Thank you for your attention. See you all in the next lecture.